So I'm gonna focus on a very specific problem and tell you about all my work about the calibration of the MFD, how we should calibrate an MFD, and what are the issues that you may have when you do the MFD calibration. Yeah. Yeah. So I would like to thank my sponsor. Nowadays, I'm like a sports person. So the MFD, you all know what it is. You take a network, and basically it's a curve, well-defined curve, if you do your partitioning properly, that will represent the traffic behavior in the region. And it is basically the integration of many things, the local traffic dynamics, the fundamental diagram, also the topology, also the controller, route choices, and the demand. I mean, the original paper say that it's insensitive to the demand, but that's not true. It's really the aggregation of everything that gives you the MFD curve. So you may have the regular MFD, you may have also multimodal MFD when you consider multiple category of vehicles. So for example, here you have an example when you have buses and car, and depending on the number of buses and car, it changes the shape of the MFD. You have it in flow or in speed, and you can really consider how the traffic behaves depending on the overall composition of the traffic. So when you want to estimate an MFD, and just as a disclosure, I will not discuss about partitioning today. So I'm just considering that I have an area where I want to estimate my MFD, and this area is well defined. So quick definition, travel prediction versus accumulation. So travel prediction is related to the total distance travel. Accumulation is related to the total travel time. And when you have the MFD, you want to look at the travel prediction versus the accumulation. So it's really the aggregation of everything. And one thing is important, what is important is that we have basically two definitions for the MFD, depending on which main variable we are considering. If you are considering the mean flow, which means what is in the interior within a parameter, or the outflow, which is what is the flow exchange with the other parameters. So there is some relation between the two. Still, this one only depends on the production, because this is here it's the total network length, which is fixed. Here it's a little bit more tricky because the outflow depends on the mean trip length within the parameter. And this is fixed, this may change. And it may change especially with the routing and everything that happens. If you change the ODE flow, you may also, and if your regions is not symmetric, you may also change what the triplets will be inside. So there is usually some very quick relation between this and this, but you always need to be sure that your trip distance is kind of fixed. Now, when we want to estimate MFD, so we are in the area of the big data, so everyone's speaking about doing big data analysis. But when you work on traffic, there is no real big data, to be honest. We have loops detectors, we have probes, and if you really want to go to big data, it's when you have cell phone data, but they are not that commonly available. There is not that much of big data, except with time. Because, for example, if you look at the flow evolutions, if you find the right database, you may have them for many years. So quickly, some initial definition, but I will speak in more details in a minute. So when you have loops, the problem for loops is that you don't have one loop in every links in the regions. So you wouldn't only have loops in what we call the equipped network, where the loops are. So usually it's easy to define the production and the accumulation for this sub-region. But then the question is how we scale up to the full region. So usually, and in most paper, you see this very easily scaling method, which I call now the uniform scaling, which is you just look at the total length of the full network, the total length of the equipped network, and you just scale it like that. But I will show you that it's not that simple, and this can lead to very important deviation in the estimation of the MFD. Another way is to use probe vectors. So probe is very nice for estimating the spatial speed. So the probe was really a revolution in the estimation of the spatial speed at the macroscopic level. Because, and I will show that also in a minute, when you have loops, you only have very punctual vision of what the speed are. With the probe, you really see what is the average speed within the regions. So it's very good if you do it properly in terms of speed definitions for estimating the average speed. But it's very bad to estimate accumulation and production because we don't know the scaling factor. And it's also a scaling issue because to do the scaling, you would need to have the exact proportion of probe within the region. So you have the famous fishing method that had been proposed initially by Professor Jereminis. That may help, but still, I mean, it's only gives you a very small snapshot. And if you do it and you look at the evolution of the fishing is when you have detectors, you count how many probes versus the total flow to get the proportions. But you will see that the proportion change a lot in space and time. So the scaling is really rich. Okay, so I will introduce all the different challenges related to the calibration. And in a nutshell, you can classify them in 4 categories. So the one I'm not going to speak about is homogeneity. So it's about partitioning. There is a lot of work about partitioning. The thing is, you need to have a region where the traffic is almost homogeneous. Homogeneity is debatable. It doesn't mean that everyone is doing exactly the same things. It means that the congestion is evolving in the same way in the neighborhood. So you may have links with different states. It's not important. What is important is that you really be able to draw the same overall chronology of the average speed or the average accumulation in the regions compared to others. I'm going to focus on the 3 other, even though this one will be very fast. Scalability, homogeneity, and stability. So observability. So observability is what we can see, and the challenge related to that. Scalability is when we have some observation, how we can scale it to the full network. And stability is how the MFD, which MFD should we shoot? How much frequently we need to update the MFD when we do the calibration? How can we assume that the MFD is stable? And if I start with this time very quickly, I just want to report a study that I did with my co-authors, so the Zurich group, Lucas Ambul, Alistair Lauder, and Monica Menendez. We look at 1 year of data in 2 cities in Zurich, in Switzerland, Zurich, and I don't remember the other one, to be honest. And what we do clustering to find how many MFD we can observe on a daily basis. And what was nice is that with some advanced clustering, we were able to identify only 5 patterns. And this is where the discussion with the sensitivity of the MFD to the demands matters, because it's clearly the demand patterns that are different on that days. And luckily for us, is that the demand patterns repeat from day to days for some periods. So the obvious separation is weekdays over weekends. You may have other seasonal variations. So because the demand repeats, then we can really estimate an MFD and use it if we assign the right MFD to the right moment. Or still, you may have some incidents, measure, accident, or this kind of stuff that has some impact on the MFD. And this may also create some outliers. So some days you will have a very different MFD curve because you have something very different that happens at your network level. So this is for the stability, and this is how basically you can reconnect the independence to the demands and the MFD theory, because we still need to know the MFD to make some bridge. Okay, so let's speak about observability. So first thing is that what data we have. I mean, and especially in the context of multimodality, we don't have much. For cars, usually we have loops and probes, which I already mentioned. For public transportation, usually what we have is, if you are lucky, we have the trajectory of all buses. That's when we are very lucky. But usually what we have is something which more closer to the timetables, with sometimes some information about the delay. It's not that bad, because what we need in the end is to determine the accumulation. And the accumulation of buses is quite easy to estimate. Just number of buses in operation, so you can definitely get that from timetables. But we also need to have a good estimation of the speed. And this is where it's more difficult, because if you only use the timetables, you have the predicted commercial speed, but you don't have any idea about what are the actual speed of the bus. So when you have information about the delay, it's better. But if you look at the different cities and the different open source data you may have, it's not always that we can do that. Okay, now let's discuss the main source of data, the loops and the probes, and especially the loop. Because the loops, they have a huge bias when we try to estimate the spatial speed. And this is important because the loop doesn't give you the accumulation. They give you only the flow and the speed. Also maybe the occupancy, but we cannot derive the total accumulation just based on the occupancy on the different loops. So what you usually use is the flow and the speed, and you derive the accumulation, but that means that you need to have a good estimate for the speed. And this is some of my original work about this. Very simple, but I like this picture because it really shows you what's happening. You just take a corridor, so it's very simple sketch of urban environment, and you have different signals. And what you do is, so you have many signals, and you put the loops at different locations, close to the signals, in the middle of the link, and downstream the signals. So it's upstream the signal, downstream the signals, because it's just a repetitive patterns. And in black, you have the real MFD that you can estimate with all the trajectories. And here you have, when you put all the loops at the same location, what you get. And you start understanding the patterns. When the loops are just upstream the signals, that tends to overestimate the speed. So you have an MFD, which an overestimation of the speed. When they are upstream the traffic signals, where they usually are, because most of the loops are used for traffic signals control, so they are usually there to monitor the queue. So they are usually located quite close to the signals. What you have is an underestimation of the speed. And you see the impact on the MFD, it's huge. The bad thing is that it still looks like an MFD. So if you don't have the reference, you have a nice curve, you're happy with your MFD and you think this is what you have. And then you start doing simulation, you start doing all your application, and then you see that the critical density is not the same, the capacity is nearly the same, but the delay will be different. A lot of things that you are going to predict will be different just because your MFD is not the right MFD and just bias introduced by the measurements. So now, if we try to do it in another settings, so this is recent work I did with my postdoc, and then MIT. It has been published in Data Science for Transportation, just advertising the journal because it's not well known, but the editor-in-chief are two nice persons. So if you want to have any paper related to data and you are looking for a home, just know that this is the new generation journal for data in transportation. Anyhow, so this is the data that we are using in Athens from the project Acumen I mentioned earlier. And we are lucky because we have here data for every link. So we have a good estimate of the average link speed. And we also have the loops. And we just look at the bias. So we select basically the loops that are mostly upstream the signals and the loops that are mostly downstream the signals. And no surprise here, you see that when you are upstream, so this is the ER data, so the ground truth, And this is what you have from the loops. So here you are underestimating the speed, and here you are overestimating the speed, right? So when you have that, what you think, so just small advertisement for my own work. So if you want to try to find a way to correct the bias, you can go through, try to do some analytical work to try to find the right correction factor. And this is what I did 10 years ago, more than 10 years ago. Still, I mean, to do that, you need to have some information about the signal timing. You need to know the ratio between the red and the green time. And nowadays, if you want to do that, I just ask ChatGPT to do it in a way. Meaning that you do machine learning. You just throw all the props data you have with all the loop data, and you design a fancy machine learning algorithm to do a correction factors. It worked very well. And what is good is that you only need to do it once. So if you do this for some training data and do validation, of course, but you do it for a couple of weeks, then you can use, because usually the prop, you don't have them for a long period because it's very expensive. So you just buy the data close to the loops to make the correction factors, and then the correction factors are stable with time. So you can just use the loop and the correction factors and have a proper estimation of your MFD. So so this is a theory, not very important. Just to show you the results, here you have the raw comparison of the loop speed and the prop speeds. This is the raw data, and you see the bias. And the bias is very important. This is so if you follow the blue line, you have a right estimation, and you definitely see the huge bias you have. So after we design the correction factors, and we have different algorithms to do that, you see that we can definitely get rid of the bias. So the red and the green is only the difference between the loading and unloading. Why? Because we notice that you have some hysteresis loops in the MFD during loading and unloading. And we also notice that the correction factors, it's better if you separate the loading and the unloading phase. So what's happening in terms of speed patterns is a slightly difference between the loading and unloading, and it's related to the Q dynamic of the signals because they don't behave the same. So it's better when you do that to separate the loading and unloading, and to do that you only need to have a kind of overall general idea about what are the loading periods and what are the unloading periods. So generally, when the congestion is increasing, when the congestion is growing inside the region, and when you see the decrease of the congestion. And for that, you just have to monitor the overall speed pattern in the regions. When the speed decreases, the loading, and when it increases, it's unloading. So that's the way you can get rid of the bias with the loop. But I should say that if you look at the huge MFD literatures about calibrations, most of the paper ignore this bias because what you get is just a nice MFD. And finally, also to show you the bias you may have. So let me double check. So the green is the MFD you can have in speed versus accumulation when you use the flow from the loop and the speed from the prop. So this is a reference. The red is what you get if you only use the loop for the flow and the speed. And the yellow is when you apply the correction factor. So it's not perfect, but you see that you have a much better estimate of the curve. And you see that the difference in speed is very important. So again, if you want to use it for simulation, prediction, or whatever, if you use the red instead of the yellow, you will have significant differences that you will not be able to explain. And they're only there because of the bias from the loop. Another work I wanted to discuss. So this was the loop issue. Now I want to discuss something which is really related to the multimodality, and this is some work we did with the EPFL team and a former postdoc of myself, Mandra Papuli. And we use the drone, the first batch of drone data that had been produced by EPFL through the PNOMA project. where we have all the trajectory of the vehicle within a region. So it was very precious because the first time we have everything at the same place in space and time. Space and time is debatable because space is good. I mean, the region is quite large. Time is quite short. It's only 4 periods, a couple of minutes every time. So when you look at the results, so this is here you have the different category of vehicles: car, taxi, buses, medium truck, heavy truck, and PDW. I don't remember, which is I think it's a two-wheeler, something like that. Anyhow, not and versus the accumulation of this. The first thing you need to see in this is that the range of observation is not that much. So if you look at the MFD, we didn't zoom out, but if you look at the global MFD, what you will see is only a small portion of the MFD, and it's mostly in free flow. So it's between free flow and capacity. But still, I mean, you have some interesting insight from it. Is first that you see that for same accumulation of the car, the range of the speed is not, it can be large. And so we have two colors because we were looking at what we call the running speed when we remove the stop and the over speed. So this range of speed is mostly explained by the multimodality, meaning that you need to know the accumulation of the other modes to be able to really capture this. And I will show you this in a minute. So we did some multimodal speed regression, considering all the modes at the same time. And what is important is that depending on the mode, you see that some other modes have more effect. So this is for the car, for example. Here you see that what was very important is the accumulation of buses and also the accumulation of truck. So you can really, by doing this, know which modes are more interactive with each other. What is, I think, the most interesting result is that when you compare the unimodal with the multimodal regression. So unimodal is that you just fit the car with the car, the bus with the bus, and so ever. And here is when you fit the car with all other modes, and you see the improvement of the quality of the regression between the unimodal and the multimodal one. So it's a huge improvement. So when you are in urban environment, and nowadays we have more and more category of vehicles interacting in the regions, it's very important to account for all the mode of transportation. So that's one of the interesting results. Another interesting result of this was that we tried to use another, I would call it another shape of MFD, but basically it was a theory that was introduced by Hermann and Prigogine a long time ago. I forget the year, but it was last century. It's a two-fleet model. And the two-fleet model is another relation between the spatial speed, and it's not the accumulation, it's the fraction of fraction of stop time. So how many times you stop versus your overall travel time. So you can do it in a monomodal version, or you can do it in a multimodal version just by considering the product of all the modes and the time they spend stopping. So this is the multimodal oh, the year was written in this slide. 1979. So what is interesting is that this is the best regression we can get, much better than the one we have with the accumulation. And you see that when we consider the stop time, we almost cover precisely the whole range of speed observations, both in terms of different value of the stop time, but also in the range of the fluctuation. And the fluctuations are a little bit more narrowed. And obviously, this is a multimodal regression, meaning that we consider not only the stop time for the car, but also for the buses and all the vehicles. And you can see this here. This is the classical MFD. This is the two-feed model, and you see the improvements we get with the regression, which is very significant. So that's here comes the question: what do we do with that? I mean, should we use this formula instead of the other one? The problem is, I would say yes, obviously, because it's something that's where you have a better fit from an empirical point of view. The problem is, how can you monitor the stop time first? Of course, when you have all the trajectory, it's easy. But if you don't have all the trajectory, it's difficult. By the way, I mean, monitoring the accumulation in a region is not a simple problem. But this one is even harder. And also, you know that the MFD is largely used to do traffic modeling and to do simulation. But tracking the accumulation is easier. You just know how many vehicles you have depending on the demand. But if you want to start tracking the stop time in the system, it's not that easy. I mean, you need to have a model that will give you an estimate of the stop time depending on the speed and also the demand. So formulating a model that is based on the stop time is complex. So at one point, whatever you do, you will have to have a transformation between the inflow and the stop time, or the inflow and the accumulation. And this is where you will get back the discrepancy between this model and this model, because you will have to re-estimate basically the stop time based on the accumulation. But still, I found it quite surprising that the two-feed model is the one that gives the better representation of what is happening in the network. My last part of my presentation, which is nice, I think, in terms of timing, is the problem of scalability. And I will, so it's also a paper that has been just accepted in transportation part C with my current postdoc in London. And the question is, we have a city here, Athens, and we have loops on the famous equity network. But if you do the math and you look at the quantity of links where we have loops, is roughly 5%. So we only capture 5% of the links in the network. And we want to get, obviously, the MFD for the full network because we want to do traffic simulation, MFD simulation with it. So how should we do, and how should we do the scaling? And it's important. I mean, you really need to understand that if you don't do it right, you have incoherence between your input, the demand, and your simulation. And if you don't have the right energy, just don't have the right scaling, then you may create congestions from the demand that doesn't exist, or lower the value of the congestion. So it's very important to have the exact MFD depending on the demand you are going to consider. And when you consider the demand, because some people say, yeah, but we don't really care about all this road in the urban environment. What we care is the main roads. And so if we have loops on the main road, it's okay. First, we don't have loops on all main roads, so we still have a scaling issue. But second, I mean, you have a lot, when you consider the demand and you have demand estimation, the demand comes from everywhere, including this small road. Even if they are not that important in total in terms of flow, they are still there. So we have to do something. And we have to do something right. So let me try to show you. So the problem is basically this. You want to estimate the total flow, you have what you observe, and you want to estimate what you don't observe, the non-equivalent. And student, my postdoc prepare all this. Yes. So the baseline method is the uniform scaling that I mentioned. And if you think about it, what does it do? It's simply considering that it's really a very typical problem in statistics. You have your full population, all the link, and you have your sample, what you observe, right? And when you do uniform scaling, you just assume that this sample behaves exactly like the full population. But you all know that this works well with the law of large number if your sampling is unbiased. So it is a random draw from the overall population. But it's not true in reality because the loops are not a random sample of all the links. They have been put at some places for very specific reasons. So basically, you cannot assume that this and this are drawn from the same population. And they don't have the same behaviors, they don't have the same average flow, and you cannot do the scaling like that. So basically, we tried two methods, and I think this is what was in the previous slides. So the first method is let's try to do data amplification. Let's try to estimate the flow on every link, including the non-equivalent link, but using the spatial correlation between the observation. So we use the value of run, which is a spatial imputation method. So no time element, only spatial, and we try to. The general idea is that the flow will be just like you have normal distributions fading from every point, and then you do the general data amplification. So this is the value of run. And the other one is hierarchical network clustering. And the basic idea is that you know that in the mapping data you may have from here over OpenStreetMap or whatever, the roads have different hierarchy. And we simply assume, and this was our conjectures, that if you take the road with the same level, the level of hierarchy, then they behave more the same. So we try to use the observation on the loop, and we split them in different clusters based on the classification we get from the mapping sources. And then we simply consider that all the links with the same hierarchical level will come from the same distribution. And we do the scaling. So we do uniform scaling, but within one level of hierarchy. And we separate these different levels of hierarchy. And I will show you the results of all these two methods. I'm looking for the results. Should be aware. Yes, that's the one. So here we compare the flow. Again, because we were not able to observe all the links in the system, we took all the links with some loops, and then we downgrade the observation by a fraction. So we will randomly select a fraction of this observation. So our global network is a good network when we see everything, and then we look at what we have if we only have 30, 20, 10, 5% of this observation. So there is a small bias here because in total we have 500 loops. So when we start doing something, we don't add 5% is not much loops that is remaining. So if we take all the links in the city, it's more than thousands over 500. We may have a little bit better representation at this scale, but still it shows the point. So here is when you have 30%. So you have so this is the reference and the flow estimation, and you have basically the four methods. So non-hierarchical means uniform, just the total network length divided by the equivalence. Two hierarchical is that when because usually in the mapping system you have 6, 7, 8 level of hierarchy. So we group them in 2 or 3 and see what's happening. So the green is 2, the blue is 3, and the yellow is the spatial amplification. So when you have a huge fraction of observations, I mean, you don't really need to do anything for the scaling. It works because you have enough observation. What is interesting is what happens when you start decreasing the level of observation. And just remember that in Athens, the number of equipped links is less than 5% of the total network. So it's closer to this. you see that's the evolution of the uniform scaling. So here is still good. You start seeing the discrepancy here more and more. So here we have a huge bias in the flow estimation because of the sampling. And basically the variogram is doing well and the hierarchical scaling is doing well as well. So when you have 5%, you see that's so the number of labels is not that important. The 2 and 3 is giving very good results, even if you have a very low level of observation. So that's my main takeaway here. When you do scaling, it's very important that you look at your network and you try not to think that all loops are the same, but try to find basically in which group the loops belong. So you can cluster the observation and do the scaling in a much more efficient and accurate way. And I think I have here some comparison. So for the MFD, so this is the MFD with the uniform scaling factor. So when you have a lot of loops the same, black is the reference. But you see that when you have 5%, you may have a huge difference, both in speed, but also in capacity. And obviously, when you do you apply the correction factors, whatever you apply the correction method, scaling methods, whatever the one you use, you have much better accurate estimation, especially when you have a low sampling rate. Some numbers, and this is at the very end. We did it for the full intensity. Of course, we don't have the reference here, but we can show you what are the MFD we have. So in red is the non-hierarchical, and in green is the one when you use the hierarchical methods. So depending on the day, you see that's the kind of difference you may have in the capacity. So the free flow is kind of the same, but the capacity can be very different. The critical density, also some difference. The speed, some difference. And again, if you want to do some simulation with that, you may have very different results just because of this capacity difference, because it's very significant when you look at how the traffic dynamics will behave over time. I think that's it. Yeah, so that's not that important. Thank you for your attention.
Okay, time for questions from the students. So, you know the drill, questions?
I just wonder, thank you for the presentation. I just wonder, is there any criteria to, we have different shapes for MFDs from data. And is there any criteria to choose to understand which one is reliable enough to do academia analysis?
In shape, you mean the analytical formula we use, quadratic or trapezoidal or whatever?
No, the MFD that are derived from data, from loop detector, floating car, they are different in shape.
Yeah, but I mean, different in shape, I agree. So just one example, I mean, you can have this or this, right? But the thing is that when you just take the raw data and you just plot flow versus density or flow versus speed, you will have only one shape, right? Because I mean, if you don't do anything, let's say you take the loop, you don't do any processing, you do the scaling with the ratio of total network versus accumulation, you will find one shape and it's well defined in the sense. So you see nothing. So if you fit that and you throw this in your simulation, I mean, you may think that you did a very good job, but where you will have some differences if you start doing, for example, simulation. You put the demand and you start doing the simulation, you will see some, compared to the experimental data, you will see some discrepancy in speed. You will be discrepancy in delays, all this. And this is because you miss the two important things is the bias from the loop and the scaling effect.
You mean if you have a one shape, it's actually work for everything.
I would say that
It's well defined.
it's from the data you observe, it's always well defined. So you can always find a good regression, I mean, can be quadratic, whatever, but it's you will see nothing from the shape. The shape will be nice, it will be well defined. And if you have some fluctuation like that, it may be just the multimodal effect, because if you don't consider the effect of the other vehicles, but if you consider them, you can even quietly, nicely look for these small variations. But you may still have a huge error compared to the real capacity that you cannot observe, right? Or for other parameters.
So from your experimental analysis, have you ever encountered the congested or very congested part of MFD? The majority of the diagrams that you showed are either very free flow or like this one, very, very, slightly touch the congested.
So
From all your work, not the one that you presented.
yeah, so I would say let's say if I had observed 100 cities, I think I will see oversaturation in less than 10.
And did you go further and analyze that specific days that happened, and what was the reason? Was it an accident or they regularly happen in those 10 cities? And do you have the name of the cities? Which one were?
I'm not by heart, to be honest. I need to go back because I didn't look at this specifically, but from my experience, I agree with you that this is something that we are not observing that much. And my explanation, because in Lyon, for example, this is where I made the most of my experimental work. I mean, the observation is just like that, it stopped here. And everyone knows that we have some quite heavy congestion in Lyon. And my explanation is really because of the region we are considering. Because usually, and this is the case in Lyon, when we do the MFD, we look the MFD for the inner city. So we remove the ring road because we say it's a freeway and it's behaved differently, so we don't want it. But if you look at the traffic, I mean, most of the congestion in Lyon is on the ring road because you have, in the end, a few entry points for the city. And when the congestion happens, it's just like it filters the demand to the inner city. So the congestion is before entering the city. So this is why within the city, it's not that it's free flow. It's not because we are not oversaturated that it's free flow. Because if you look at the difference between here and here, I mean, it's quite important. When you are here, you just divided the speed by 3. So it's already something in terms of congestion. But it has no impact on the capacity because the demand is filtered. So it's not possible to overflow your regions to a point that it will be that much congested. So for example, there is no need for perimeter control because there is yes. Still, there is one thing which is that I also observe. If you take a city like Athens with that, and you start doing smaller regions, you will find smaller regions with oversaturations. So it's usually the full city MFD that are not where you don't observe the oversaturation.
Thank you for the presentation. For the hierarchies, how did you define them? Is it like the different kinds of heroes or constructors?
No, the hierarchy is really, I mean, if you look at, you go to OpenStreetMap and you look at the link hierarchy, you will find it is 1, 2, 3, 4, 5, 6, 7. 1 is freeway, 2 is main ring road, 3 is arterials, 4. So they are doing some magic there because the difference between 3, 4, 5, for example, is not easy to. So they say that they use some advanced techniques based on the observations. So I think that they already do a little bit of clustering based on their data to put the links that are the same in the same category, which is good because this is exactly what we want. So there is no surprise that this hierarchy works very well with the scale.
Yeah, makes sense. But also, like hierarchies in Milan are like freeways, arterials, local roads, or something like that.
Yes.
And then why don't you consider like maybe the design capacity for the freeways as one scaling factor, or maybe make it continuous instead of different classes?
I mean, first again, I mean, so the ring road and the freeway is not there. So it's only so if you look, we have arterials. They have two levels of arterials, and then secondary road. They have two levels of secondary roads, and then they have the minor roads. So when we leave the two, it's just the arterials and the secondary roads, and the three we put the small one as well. We could have refined indeed the definition of the scaling, but considering how it works, there is no real need to do more than that. And I think it's because, especially here we were using the here data, and they are doing this in the advanced analysis of their observations to classify the links. And this is why when you plot the results on the map, sometimes there is no sense because some links that are very close at different levels. So I think it's really based on some traffic information that they do the classification, and maybe they are using the capacity or the number of lanes or whatever themselves to do the classification.
I think for presentation, like in terms of the scalability, like is it possible to consider scale up like based on from the point of the similarity of the network structure?
I mean, everything is possible. I mean, if you understand the underlying principle, which is you want to apply the law of large number, so you want your sample to be representative for your population. What you need is that all links that you don't observe that have the same behavior be assigned to the loops observation that are the closest to this. So you have many links. You need to find a cluster where the loops will be allocated to the right cluster. So what you observe in your sample is the same of what you observe in your population. So that's the principle. So you do whatever you like to get there. And it's happened that the hierarchy in the mapping was doing the job, but everything else can also work.
So we have the comment more on Zoom chat. We have like 6-7 people joining there that they were mentioning that Brisbane is an interesting place to try this stuff as well, because they have like extensive Bluetooth travel time system, and also the bus network is fully instrumented. That's just a comment. Maybe for your time.
Bear with me the data, and I will give you the review.
So okay. The big part of changing my question is, what's with the future of MFD? What else is remaining? Yeah.
So you mean what will I do for the next?
One part of your research or the research community on MFD, what do you think is remaining or untouched, or it's done, let's move on, or what's?
Okay, so I will not disclose all my little secrets.
Yeah, you don't expect to have your secrets, but what's?
I really think that I mean let's call it the main limitation for me of MFD is that for now we don't have good. I mean, we can observe MFD. We know from the data to get an MFD and do some things. But if I give you a new city, and I tell you, give me the MFD, we don't know, because we have very little methods to estimate what would be the MFD if we have a new design, a new topology, a major change in the public transportation or whatever. And this is a very significant limitation, because we cannot do anything in terms of prediction of future plans. And nowadays, I mean, especially if you think about all the transformation related to massification of transportation, related to climate change, everything we want to do in the urban environments to adapt the city to the climate, it would be super nice. The MFD could be a super quick tools to assess what will be the performances of the city, the dynamic of the city, overall dynamics. But we don't know what the MFD will be. So I mean, so that's for me a huge limitation. The fact that we can only predict when we observe. And of course, you always got the guy that work on perimeter control and that wants to be.
I don't want to go to the okay, good. So let's thank you again for your presentation. Thank you for joining on Zoom and